Okay, so welcome everyone to this new episode of EagleFly, the experimental debugger. Today we will continue making this awesome debugger, and if you'd like to follow along, please don't hesitate and welcome. If you have any questions, you can post them on Twitter or YouTube and I'll be there to answer. Alright, so let's open the project. So you remember, well, I already opened the debugger. If I run this, we make some kind of, the last thing we did was we started to expand the disassembler to other instructions, such as the shift left double and with 3 operands, and the first instruction, the add EAX, add memory to EAX, which is another instruction as well. So that's the last thing. We added that loop, which we just go and follow along. So I think that's good, and we can continue doing the same stuff, today, and pretty much do the same thing we were doing throughout all this time. That basically is to go instruction by instruction being built in the disassembler, which it's something that works, if you see. So let's go and do exactly that. I will open the project. And let's see, we compile. So let's go into the code. Shall I remember where it is? Let me see. Here it is. We set the for loop in here. So let's go now and disassemble another instruction. Let's see, we have a bunch of instructions to choose. So let's see. One thing we can do, and I don't know if well, we can do it right now or in another moment, but this is quite nice because this tells us which segment register is using to gather up the memory operand, which we can know on the coding itself, which is rather the DS segment or the SS segment. Those are the two that are used normally, and yeah. Okay, so let me see. We haven't added mandatory prefix usage in here because, well, any of the instructions we have used use them. So but if any, it should become before the REX. Yeah. Now we have to be careful about the 66 because 66 is also the operand size of the right prefix. So for knowing what is it exactly, we have to make something clever here. But let's see. this is a shield instruction. Let's go to the 3-byte thing. And the instruction we're going to disassemble now, it's a 3-byte thing, which is OF3A. Okay. So before okay, this is the 3A. We're looking for OF, which is this PALIGNR, or we have PFX 66, which I don't know what it is. That exactly. It's a prefix. Oh, prefix. Okay, yeah, prefix. Yeah, it has a mandatory prefix. Oh, okay. So the table encoding indeed has a mandatory prefix. Okay, so we have a mandatory prefix of 66. So it should be PALIGNR. So this is interesting because even though we have a 66 prefix, we don't have a, well, let me zoom here. We have two instructions here with PALIGNR and the VPALIGNR, which either this is a vectorized way to look at it. Let me find out. Okay, this is BX. And normally, yeah, the VP line is for BX. Concatenate XMM2 and XMM3 M1 to A, extract by a line, result shifted to the right by constant value in immediate A, and result is stored in XMM1. This is for ABX flag 12, ABX, and normally P line is for SSC3. Okay. So MP is no prefix, 66 prefix, escape opcode OF3A, and the OF normal thing RRIB. The difference between these two is one uses MMX and the other uses XMMM registers. So the destination operand is XMMM. This is the source operand by immediate. Okay. Which in this case I guess it can be XMMM2 and 128. Well, this is its data size, isn't it? MMN2, M64. Because, where is it? If I move this a little bit in here, we'll see that, yeah, we have XMMM. Oh, but we are this is moving from XMMM1 to XMMM0. Probably that's possible. This, I mean, I thought it was like this should be this way. Probably it's not. Yeah, okay, this is legacy SIMD instructions operating on MMX registers. Okay, so we done. Yeah. I mean, we don't care too much about this. It's even though it's important to know this, but yeah. Okay, let me go back to the Beeline thing. I was just trying to see the description of it. Okay, so RVMI and FVMI have 4 operands. The one we are disassembling has just 3 operands. Okay, mother RAM, rec, RW, mother RAM, RM. This is on the rec. The other is on the RM, and the other is on the immediate thing. And that's it. Okay, ships at by granularity to the right. It tracks the right aligned result into destination. The immediate value is considered unsigned. Okay, yeah, 16 bytes. Okay, this is interesting. So you can set something to 0 by using this instruction. If you shift to 16 bytes and you're using 64-bit operands, the result will be 0. If you use 128-bit operands, you will need to shift by 32 bytes, and the result will be 0 as well. That's interesting. Okay, when the source operand is a 128-bit memory operand, the operand must be aligned on a 16-byte boundary. Use the RX prefix to access additional registers. Okay, so we can use REX when not using EVX or EVX. Okay. What? I thought it was totally different, but this image tells me everything. First, it shifts by immediate to the right. Um, uh, uh, and if you see here, we have 128, 128, and this is 128, 255. Now I don't understand. I mean, this is the first and this is the second operand, or this is the destination. Here is, I guess, shifting by this quantity, which of course it has to be, but it's bytes, so the maximum it's 256 bytes to shift. So right there is shifting by some amount, and the other source is shifted by the same amount, and it's going to pack them just as if from source 1, the first source is gonna go to the high part, and the second source is gonna go to the low part, shifted. Now the shift is a little bit weird because it should go to the right, but this seems like shifting to the left, you know, or at least that's the idea that I see here. Probably it's to the right. But no, look at this. First concatenate destined source into a huge thing, and then shift it by immediate count to the right, and then the temporary for this 464 is gonna go to this 107.27, and then the dest is gonna be the 10.106. Okay, this is the thing I was expecting, you know. This is the thing that I understood the first time. This image, it's a little bit weird because it seems not to be there. PLN we want to be band when we want to be operands. It's gonna be 10.1. Dest shift to 128, or source (127), shift to immediate. Okay, this is a concatenation. at 255. The desk then gets the 127, the low part, and then the destination from max VL minus 1 through 128 keeps unmodified. Now I don't know what max BL is, but it should be some boundary. It should be yeah, that keeps unmodified. BP line 128. This is the other one. Is source 127, shift to 128. The same thing. Source 2. Oh, okay, since on BP line now we have 4 operands, we can use 2 sources. One shifted to the right, or the shifted to the left. Sorry, it's the same concatenation. Shifted y immediate by 8. Immediate 8, the same. Story on the temp. Just keep the temp with the inside the desk, and then pretty much the same stuff. Keeps. Oh, okay, I see the difference now. BP line is gonna. This is gonna be kept unmodified from the desk max BL through -1 or 1 through 128, but BP line is gonna set them to 0, which is interesting. Okay, so there's like these differences across the instructions. Of course, the one that we are using right now, that we are disassembling, is this one. So it's not. This is the thing that we should expect this to do. Okay. Okay, so let's disassemble it now that we know what's going on with that. Okay. So let me align. So we're gonna have a mandatory, well, it's not a well, yeah, it's a mandatory prefix. So let's encode that here as well. Where is it? So pretty much this is the same. Now we're gonna define this mandatory prefix prism. I don't know if we can have more than one mandatory prefix. If we do, we probably want to be moving around. The mandatory prefix, if makes sense, it should help us. But if you see here, where is it? 3 by here on the BPL line thing, we don't see. I mean, the BPL line is with 66, but the PL line is also with 6. I mean, I don't understand this prefix thing, because we have to look to the BX and see if it has 66 as well. But yeah, I mean, probably that's a kind of bogus thing. Okay, so yeah, I mean, pretty much is to skip them. This is gonna be the same. REX. Right now we haven't checked that for escape opcode person. We have an escape opcode. And if I go to it, we do have that. And we do have as well other information now. We have 3/8 and 3/8. That's gonna tell us if we use other tables as well. So it's a combination of them. So you can just say So we pretty much have 3 combinations. So I guess we can do that here, you know. There's no means why not to do this in here. So we can just say how you call this, do So now I think about it. Well, right now I'm gonna keep it here, but I'm gonna put it to here. So that's pretty much it. So we can go and check that out. Oh my god. There you go. So we haven't done that yet. So cbyte, it should be the mandatory prefix. Yeah, 626. Okay, so let me just do that before. Anything else? We do have, there we go. There, oh my god. The entry is null, perfect. That should get working like, once again. So the cby should be 15. Okay. We have OF 3A OF. So, well, wait me a second. Yeah, of course we haven't initialized that yet. Now I want to assert that we got the tables, so we can just say I can assert or just make the check-in. I think this is better. Alright. So then we pretty much need to just fill it in and do the well, the filling of the table, I guess. Let me see now, just for me to check that. Probably I'm gonna put the, well, this is the I'm gonna change it. This is gonna be load tables in here, which we probably can do. But right now we don't care. Now let's go and fill the table so we can just do the same stuff and say here you go. So you see here, well, we're gonna make a for loop or something. This is the PALIGNR. It has some other RAM. It's rectum other RAM. I don't know. We should check that. I believe it is PALIGNR VX. since it's not a general purpose instruction, so it's not here. It should be unnecessary, I guess. General purpose PALIGNR. Promoted vector insert SIMD. Oh my god. PALIGNR, there you go. We got it. PALIGNR packed line, right? This is the encoding for the packed line, right? Rec2 to rec1 immediate 8 mmx. Okay, register. It's like rec. What's xmmrec? rec2 to rec1, rec2 to rec1, or from memory to rec. Now the one we are looking for is the register one, so, and it's the second one is this one, rec2 to rec1 immediate 8. This is gonna have this is 66, and then OF, and then 3A, and then we have OF again, because this is the main of by. This is the mother RAM, rec1 and rec2. So, and we have an immediate just afterwards. So we know that there's these two. Now the sign bit, the direction bit seems to be set, so that means that we are going from mother RAM to rec. You know, now, yeah, so mother RAM to rec is gonna be false. The immediate size is gonna be data size byte. Yeah, we do have one. And operand count, it's 3 as well. Yeah. The mnemonic count, mnemonic name count, string length, shift left string, it's gonna be a PALIGNR. Up table count. Oh my god, what's going on here? It's a bug. There you go. There you go. There you go. Now I don't know what else we were trying to do over there. Probably that's all we need. We just initialize another entry in there, and we just say that the 3byte to table 3AH is gonna be pointing on to there, you know, pretty straightforward, and pretty much that's gonna be the thing. Alright, so now if we do the same stuff again, we should, oh my god, we got the entry. Let's see, we go, and there we go. Now this is pointing towards nothing. That's a little bit weird. So let me, where is it? Initialize a table. I'm gonna set a breakpoint in there. There you go. We have a table count. We initialize it. Oh, my bad, my bad. I was like, what? Of course, we have to point to the right thing here. Alright, there you go. We have there's size by mother and preset, rect to mother m is false, encoding index is 0. Well, that's, we don't care about that. Running, we don't care about that. We don't care about that. The P line, yeah, we don't care about the P line and the P line. So we go straight on. to the place where we used them. So table should be pointing towards there, and we do them. We got everything right. Now the main bytes pointing towards somewhere. Let's go and look at the plate. OFC1 OF. Okay, yeah, it's the, now this is the main byte, C108. Perfect. And now let's go into there, blah blah blah. For now it's gonna be okay. Table index to result. Perfect. We got entry mother % extracting operands. There you go. File pointers, C byte. Now one caveat that we have now is that we don't modify that, so let's try to modify. C byte is still pointing towards the place, so we can have a bunch of pointers, you know, but you know, sometimes it's useful, sometimes it's not. For example, right here, whenever we get to the C byte, the C byte is gonna be pretty much, we are assuming the C byte here to be on the, rather after the mandatory, after the REX, you know, if any, and after the, I mean, it has to be on the escape opcode or on the main opcode, so that's the way it goes. Now the main byte here should be modified as well, so we can have this like this, if you think about it. I don't know, that's the best way to think about this. Another is to have a mother and byte being yeah, this thing right here, we already have one, so we can pass it and be the one we used. Because pretty much that's what we want. And begin operand extraction, we use the mother and byte. I think that's good. And since we're moving the C byte like along towards this, let's see. So let's stick with 1, because that's the way that we are looking at here. If we see that there's a lot of problems with that, we can just skip that way. Now just like the same thing. Now I don't know if that's better. I don't know if it's too hidden, like, hey, we're modifying all this stuff. I mean, it's probably the thing, because we are like, go step forwards. Just give me the address of it and I will manage it for you. I will return it so you can plug it into the thing that we have, you know. Yeah, I mean, I don't see any problems with that. Per instruction, in any other case, we just be moving the C byte to the next one, because that's the way we do it. That's okay. And here it's just gather the data out. We don't need to do anything more than this. So pretty much when we finish this, the C bytes pointing to the next instruction. So that's good. So what about that? If we do it that way, we'll get C bytes. So this is gonna be like this, and this is gonna be so it will be something like that. And then we'll just use it the same way as before. So we use the C file pointer. Which is alright. I mean, this is okay. I don't want to have like this byte direct reference if we can avoid it, because if you think about it, we don't need it that much. I mean, since it's better to have like offsetting stuff like that. Effective address size +1. Okay, so yeah, I mean, this is all using the operand offset, and finally we just return that, you know, on the end thing. Yeah, so I like that more. So if I go into the begin thing, say, well, you know what, just want to pass that, and this is like that. This is pretty much, yeah, I mean, it has a contention there, so I like that. So the communication, it's explicit, like, hey, we finish, we give you the pointer where you have to continue. If we don't do that, we just continue. This is, I think this is really explicit. Now for this case, we can do the same thing. Yeah, we can even pass it, because since we are not getting like a lot of things, I think here is okay. Still we can just do it, but for now it's okay. So you can do that thing like that, and that's it. So let me go to the entity and see what happens in there. Now we just copy this stuff, and finally I want to modify the current pointer to move to the main of by, if you think. See by. It's gonna be main of by +1, and that's it. Yeah. So we do it that way. We can just say, well, let's go back, let's continue. We pass the address of cby, and with the references, and we store it as well. Yeah. So we're just going to do bananas in here, moving around, the same stuff happening. We get the index, we get the result. The main of by +1 is the value that we're going to store afterwards. So this is going to be the thing now. Return the result, entry. So if we see cby, it should get modified. Now it's pointing towards some value there, which is C1, and C1 is the mother and byte, which is good, and that's it. So yeah, we do have that. We begin, we get the C by. Now this is the mother and byte, isn't it? I don't remember. Let me see. Yeah, it's the mother and byte. And okay, yeah, because we were expecting it to be not the mother and byte, but yeah, I prefer it that way. So that's better. So over here, where is it? In begin operand extraction, it's gonna be like that. That's it. And that's pretty much it. Once again, we try to do this. 5, 5, F10, F10, F11, blah 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 blah. Let's see byte. Yeah, that's correct. We fetch the memory operand. In this case, we don't have a memory operand, and that's important. That's good because this should pretty much tell us something about that. Motherand byte 630. There you go. We got the values. There you go. Motherand byte. It's the motherand byte, which is the C-file pointer. There you go. If the motherand byte is now the C, which value it is 193. Motherand byte on the hex, it's C1. So let's go to the table for the motherand. And it's, if it's C1, okay, so it's a register. That means that we are getting onto a register stuff into there. So this is gonna be C1. It's gonna be direct fill. It's some value from here, and the motherand it's some value from here, which is that. Now, one thing that we are missing now is that the encoding itself, it's telling us something about the size that we haven't thought about it before, because, well, we haven't thought about it. So we are gonna say that, well, what is it? We can do it here, I guess, and just say, well, I'm gonna have a entry thing. There we go. And we're gonna have a fly up entry. Okay, so if we do it that way, just say entry 0. It's gonna be current entry. something like that. And we just say, well, we're gonna use the entry because the entry is gonna have some parameters that we're gonna use for the coding process. For example, the operand size. The operand size, if you remember, we overwrite it every time. So now I think about it, well, this should go into here as well, because this is independent for each instruction. So normally it's gonna be this, but yeah, you can do that. The REX is gonna override that, but there's instructions that they don't care about that. You know, it has to be one operand independent of the size override stuff. You know, so that's important, because when we start to do the instruction here, we should have the real data information about which is the size of the operand. So the entry can have that. We don't have any reasons not to do that. We can have any more complex stuff, but for now we don't need it. It all depends on the thing we want, but for now it's okay. You just pass the entry and that's alright. So if we pass the entry this way, we can go to the fetch memory operand and start playing around with that. You know, so we're gonna say, well, you know what? Right here we find a fly up button, fly up table entry equal to the system state G entry. There we go. And pretty much we do fanciness with it. We're just gonna start by saying, well, if the entry, where is the overriding thing here? Model by, this is gonna check if we are looking at the okay, I'm gonna pass it here, effective operand size, you know. There we go, I like that. We're gonna need it. And then we're gonna say, I don't know, why do we have this? Probably we're gonna need it, but well, if we don't need it, we don't need it, isn't it? We haven't got the point where we need the SIB, but we're gonna leave it right there if we need it. Okay, so we got that, the rect instruction, the construction, it's happening there. Now we can say if entry we can say which is the one, it's the both are registers, that means that the mod it's encoding that, and we can just find it out because of the mod itself, because the mod, well, the mod RAM is telling us, well, you know, if the mod this is a special, this, let me put it here, note memory extraction. So we can just say if let's simplify a little bit this, if modern by blah blah blah, we have address size blah 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 blah. Okay, this is good. Now over here if model RAM is greater than C0, well, I can just copy that. And say, and this is C0 FF. We just go and say, well, you know what, we are not gonna do anything of this, but we are gonna fetch a register open with the data information, blah blah blah, we don't care, and that's it. We can just say that this is a register, so we just say, well, boom, something like that. Now this can go until pretty much here, I guess. And say, well, we're gonna fetch them and we're gonna say, well, you know what, this is the thing. Let me see what does the fetch memory register operand needs. We need the disassembly state, rec buffer, which is the same. This is the buffer size, effective operand size. There we go, perfect. And that's it. Now the fetch is gonna return us something, which is the buffer count. So the result should, oh my god, should be that. Well, this I guess is like that, and we return it. Okay, so let's compile that. C entry, we don't have any C entry. Let's go to disassembly and create one. I mean, result, it can be like a little bit conspicuous here because we don't. Okay, I'm gonna change it to buffer count. This is the buffer. This is like that. Fetch memory operand does not take 4 arguments. That's true. We need the effective operand size as well. Right, compile back. Perfect. So now that we have that implicitly, we can just go and do it. Pretty much the change here is that, well, on this side, we're gonna go and fetch the register operand here, and the register, it's gonna be, we have to pass, okay, it's pretty much the same stuff. This is gonna be, yeah, we're looking at the same thing here, mod rec rm mod rm byte. We do the same deconstruction, and let's see if it's gonna reverse unit 32. I'm gonna call this the offset. Now this is looking at the rec. We have to have an option to look at the mother arm as well. So this can work without the notion of this. We just pass. Well, it's the same, isn't it? It's the same, but the look is different. I mean, one is the rec and the other is the mod, So the mod, we don't care too much about it. We're not gonna use it here, but we need the rec or the RM. So that's the thing we need. So either we pass it here, which I think it's better, So this is rec value, I guess. Rec. Or we can have it like as an aside one, which, well, it's not too bad. We can have can say I don't know, let me see. Now the row can be 0, so it's more like this, I guess. Okay, so the reg, so we can just keep that way, fetching data, and the reg should be well, in fact, you know, we can keep it the same way we had it. the way it goes. So now we fetch it, we go find it out just as before, and we just say, well, you know, we got a mother and by, and yeah, I mean that's all she said. You can't even assert here that we have a mother and by, because we should have a mother and by. If not, well, it's bananas. What else? So let's run this. Okay, that's good to know, because the default pointer is pointing to something. Now, yeah. That's totally true. That's a totally reasonable thing. But the default pointer now, it's not the thing that we were thinking before, you know. Because default pointer, even though it keeps track of it, now we use it as a temporary thing instead of absolute, well, general stuff. So yeah, I mean, we can have the cby being from disassembly as well. You know, right now we have a cby, but the cby is it's just on the stack being moving out. Right now we don't have any problems with that, because everything is on the same function frame of reference, so we can keep it on the stack, and anything will be okay. But yeah, I mean, we probably want this to be the same state, you know, because this is more like the thing we want. Of course, for simplicity, we're just gonna have it that way. Now this is gonna be like this, of course, and I'm gonna call this transition by pointer. Yeah, I mean, we have C bytes, where is the C file pointer stuff happening? So I mean, in the future we are gonna use this. Right now we are not using but one of them. So let's say, well, with C by it's gonna be just the same as this thing here. So it's more like that. That's okay. uh, yeah, well, for now, I'll think about it. It's better if you keep it the other way around, because just for taking complexity out. If we have another frame of reference later, we can just store it. And this is just gonna be that, and this is like that. we are gonna do the same here. Model run byte. It's gonna be that. Okay, we're gonna fetch it with that model run byte, effective operand size. We just gotta reverse. We do the same stuff. Fetch model RAM. Fetch model RAM should be true. Yeah, it's true. So we got from the RM the data that we want. So row it's 1. So if it's 1, we should go 9. The offset is 2. Boom, boom, and the operand is ECX. Aha. Which it's okay. The only problem, of course, is that the effective operand size, we haven't resolved that. I'm sorry. Okay, that's good. That's perfect. It worked. The only thing we're missing, of course, is to resolve the effective operand size. So the effective operand size, as we see it here, where is it? Fetch memory operand. Here we have to resolve it, of course. After this, I don't care about that. Let's say entry operand info blah. Well, this is the now we need the operand info, isn't it? Because the operand info is the one that we need to store or to get data from. How do we want the operand info to work? We can use the same stuff we were doing before. Let me think. So we know that the rec this is the PALIGNR. You have a PQ, QQ, and IB, which means, where is it? Here we go. We have a P, which is the rec field of the model RAM, but selects a PAC-WAC4 MMX technology register. Is that correct? Let me move this around here. Move it that way. It is. We have VDQ, WDQ, IV. Okay, that's not correct. This is this is not the VDQ we're looking here. That's totally weird. Is this wrong? Because yeah, we have OF3A. In row 0, column F. Yeah, we do. We have a PALIGNR, but we don't have a. This is a PQ, and this is a VDQ. That's weird, isn't it? This makes more sense, but we just have 3 operands: VDQ, WDQ. Now P tells me that it's a quad word MMX technology register. So this is, oh my god, where is it? So yeah, we are looking it wrong, because this is the MMX one, but we have to look for the XMMM one. You should remember it was this one, which is OF, and this is 3.9, no 3.8, sorry. This is totally wacky. So the table is wrong? Yeah, it's totally wrong. This is OF. Oh my god, so it's totally wrong. Oh my god, so that sucks. Okay, so okay, VDQ. No, but this is another instruction, but it has the right operands. That's totally weird. This is 3.8. Yeah, this is not gonna be. That's totally weird. it's because, I mean, we are for sure that we are looking. This is the MMX one. This is the MMX, but the XMM, I don't know where it is, because this is BP aligned with 4 registers, which is not the case. It does have 66, so if it's VX, yeah, look at this. I mean, it's not on the table, but it's on it's right here. 66 OF 3A OF IV. It's an XMM P line or okay. So it's really similar to this one, XMM12, blah, 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 but this has another register, XMM3. So yeah, I mean, this is more like the thing we have to look for, EVGV IV. I don't know where the instruction is, but it's not on the table, so the table sucks, so we have to find it out somewhere else, so whatever. So if it's a B, the right field of the motherboard byte selects a 128-bit XMM register. So right here we were looking at the mod RAM. So or memory location. So we are looking at WDQ. Now this can be misleading because I mean we are looking at the memory. Normally it will be, I mean most cases it's gonna be memory or register, but it's more like, yeah, I mean it can be memory or RM operand size, but the entry is not gonna care about that. Well, memory operand size is okay. I mean the references are good, you know, that's what I say. They are good. Memory operand size is gonna do that. Now this has a caveat, of course, that some cases this should apply, some cases it's not. So it all depends. Yeah, because if you see here, it's because of the DQ we are using the regardless of operand size attribute. So it's more like um, well, I'm gonna keep it that way because right now it's okay. Now put a to do here. Check if have a way to, it's more like a size system. Like I want to define a size system, have a way to override it, have a way to so the memory operand size is something that we're going to store, of course. So I can do the other one as well. Rec operand size. And let's go and fill it in as well. So let's see, over here we're gonna have that. This is MMX. And the shields should have as well something here. For example, this is gonna be it was EAX, isn't it? But this is for memory, so memory yeah, because it's gonna fetch memory here. So data size max, data size, this is a shield entry. Probably, well, it's a U32 displacement, but that's on the mother end by. We don't know the displacement. It just tells me that we have a general purpose register, if it's a register, if not it's a memory operand. So it's a memory operand or whatever. Now we don't need to encode that, we just need a default, I guess, data size. If we don't have it, we can just say, well, because a general purpose register is not gonna tell me pretty much a lot of it. So yeah, data size invalid, I guess. And here as well we can have it, the shield entry, well, it's gonna default to invalid, so yeah, I mean, we can just fetch, if it's invalid, well, we're not gonna use it. Well, let me write it because it's important. Now I put it data size none. We can pass it to invalid, I guess. Data size invalid. And this is the same. And something like that. And something like that. Alright. So let's go and play that again. So the effective operand size, it's 4 for now, but we got an entry which should be having it has a quart. Do we say a quart in it? Oh yeah, I'm sorry, I'm really sorry, XMMM. I'm really sorry. There you go, one more time. we go we go and fetch it, their entry, there you go, it should be XMMN now. Yeah, it's an XMMM. So we just say, well, yeah, it's gonna be that, blah 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 blah, and we say, yeah, effective operand size is now uh 10. Is that XMMM? Are you serious? Are you serious? Let me change. Okay. Oh yeah. No, my bad. Because I was like, what? I thought it was looking binary, but it was hexadecimal. Yeah. I'm sorry. Yeah, that's correct. Okay, good. And then we just say, well, we're gonna go and fetch it the same way. Effective operand size, we just do that. The bit info set, we just have an information for that. We go and fetch from the RM in this case, and the offset should be 4. Okay, so the offset is 13, which now makes a little bit more sense. And this is XMMN1. Perfect, that's the thing we were looking for. And we just push string to the buffer, which is gonna do craziness. Yeah, the same stuff. Well, yeah, and the buffer should have the data information into it. Let me see it. Yeah, XMMN1, and the buffer count, well, it should be the same 4. Okay, perfect. It's really good. That's really good. Fetch register operand. It's gonna got buffer count. The buffer is gonna be fill, and yeah, return buffer count. Here we go. Buffer count. It did all that data information in this case with a 4. Good. Now the second register is gonna do it. Now it's gonna be false. Effective operand size, it's 4 now. Okay, yeah, because we're using the one from the big hole. Okay, I think that's good. Yeah. Okay, because I was like, yeah, from the stack information we're getting from the big hole, so that's good. So big hole. Well, from the general part, because the frame stack we're getting from, if you remember, we fetch it, but the other information was overridden because I mean, we're all getting, this is the effective operand size, the initial effective operand size, and that's the one we want. So that's good. We're gonna do the same thing, the composition. Now fetch tomorrow RAM should be false, of course. Yeah. So we're getting from the rec field, and the rec field is gonna tell us as well. You know what? Well, whatever, the offset should be 2. And here as well we have another problem because this as well have a rec operand, so it should be XMM1, I guess. Yeah, XMM0, sorry. So we fetch for WDQ, which is the RM field with a NEC 128-bit XMM register or memory location. So yeah, and V tells us that the rec field has a 128-bit XMM register. So just as well in here we should do the same for where is it, the shield and entry. Perfect. and this is the rec operand size. My god, rec operand, what, register operand size. Okay, my god, register operand size, there you go. This is the same in XMMM, being forced to XMMM, so that's good. And for the other ones are invalid. Well, the rec in the other cases, well, let me see, so I can fill it out as well. It was a general purpose register. It doesn't tell me anything about the size. Let me see. Yeah, because you have EVGV, so E is from the memory thing, and it tells me that a general purpose register or a memory address. In this case, it was a memory address, so we have that to construction. If it was a register instead, we will need to fill it in with, if it's it's computed from some register, okay. So it's taken from the general, it's the data type. So V, let me see, V, a word, double word, or a quad word, depending on the operand size attribute. Okay, so well, it's the operand size attribute that defines it, but the operand size attribute, it's, if you think about it, well, there's nothing that tells us anything. I mean, right now, on the way we have it for the REX prefixes and the operand size attribute resolution, we just look for prefixes to define that, which we thought it was the all the necessary stuff to define that stuff, but probably it's not. Probably we need something else. Now, here, I mean, we do have this information, but this is more like, since it's too general, I mean, it's not defining me like, oh yeah, it's this stuff. So that's the kind of problematic stuff to encode it. So for B, it can be a word, a double word, or a quad word, and this is the operand itself. It's not telling me, oh yeah, the address size attribute. The quad word, of course, it's only able to be encoded for 64-bit mode. So basically, we're looking at word or a double word. So how do we know it's a double word? Well, because the operand size attribute is telling me that specifically, So the effective operand size attribute should be encoding there as well. So yeah. So if that's the case, I mean, it would be yeah, these are, so probably what we find is more something like this, like, let me go to the place where I was looking at. I'm gonna say something like this. It's because even though that's not, oh, it's a little bit hard because normally it's gonna be 64 fade 2, you know. So whenever we are in that range, everything's okay. We can go and fetch directly to the operand size attribute. But when we have like this kind of craziness where let's no, this is floating point. This is a quad word mmx 128b or 256b. Now, yeah, I mean, I want something that depends, that varies, you know. So let's say wide bubble word or quad word paint. Yeah, for example, this one, it's a specific on the operand size attribute, but the operand size attribute has to be resolved so that it tells me that it's a double word or a quad word. Now, it probably is that for y we are just looking at let's see, where is it? I want to find somebody that uses y itself, which is not like too hard to find probably. For example, this gy ey, we know that these are SIMD instructions or vx or whatever. These are SIMD, yeah, they have to be SSC something. So yeah, I mean, they have to have, if they are SIMD, most of the time they're gonna be double words, no, quad words, or 128-bit or 256, or I mean starting from 64-bit. So probably that's something also that defines it. Because, well, we can say something like this. This is XMM and this is it's a word. Yeah, that's a little bit tough, but I'm gonna hold on to it just for a second. Let me compile that. Thank you very much. There you go. Okay, so we have an XMM. So over here, the resolution is gonna be that. That's good. You got the entry. That's good. We define an entry. That's good as well. So the fetching is gonna have some standard information. Now we have to do something clever with this. Right now we're just doing that, so that's okay. That's gonna work for now. But yeah, have to do. Yeah. So I'm gonna do that way. Let me do this once again and see if we printed out something, you know. So let's go. Oh yeah, and did we set the register one for the other one? The register it's XMM. Oh yeah. So oh yeah, I'm sorry. It's because I I forgot that I was doing something, but then I started thinking about the other problem. But yeah. Yeah, the thing I was mentioning, and I was like trying to do here is like on the fetch register operand. Whenever we pass to this one has to have the effective operand size correct. You know, so yeah, yeah, the resolution has to be something here, but I'm gonna do the stupidest thing here as possible just for now, which is gonna be the pattern for the solving of the general question. But for now, it's gonna be if entry rec register operand size f operand size equal entry, which can be a ternary here. I'm gonna do it as a ternary for now. And that's it, you know. Yeah, yeah, I mean for now it's gonna work, but yeah, we have to think about that. Okay, so let's run this one more time. We found out the first one, which is buffer A, or mem buffer, sorry, mem buffer xmm1. Right here, let's enter into here, and we say effective operand size is 16, which is good. The effective operand size, blah 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 blah. Now from the row, it's 0. What? Oh yeah, so the row is 0. Yeah, that's correct. So the well, it's good. Yeah, we have xmm0, which is correct. That's the thing we want. We push as well, and we return. So we have 2 operands now. That's correct. And then fetch immediate operand. We do have an immediate. We do have an immediate. Yeah, we do have an immediate init. Yeah, yeah. Okay, perfect. Okay, perfect. Well, I don't know if I have it, but what? No, that's not correct. That's not correct. Let me see once more time. Oh, because we didn't move the pointer. Yeah. Okay, okay. So let's solve that as well. So let's solve that as well. Now this is gonna be like this. We want to move the operand offset by something past, and this is the mother. Yeah, we use the mother m, and that's it, isn't it? So so we probably want to do Yeah, because we're already on the mother and by, so we should be just the C of by is on the mother M, so we just move by 1 and we'll get to the immediate data information. But this is because we are fetching the register, so we have to do something more clever there. But yeah, so operand offset is 1, operand offset is effective address plus 1, so yeah. Now this can be like this, because the resolution should happen in here. No, well, yeah, because probably we're gonna find out that on the rec field we're gonna move it, we're gonna have to add it as well, so it's more accumulative. It's better to have it a cumulative way, probably, I don't know. Well, let's say we have that operand offset, yeah, this is correct, right. Okay, so we go and do this effective operand, there you go, we go operand offset, there you go. So the operand offset is 0, there you go, buffer cam, boom, we go fetch the register operand. The register operand is encoded into the rec field, so that's okay. So this is, we can just pass by there. Now the immediate, let's jump into it and see what happens. That's correct. Oh, hold on my second thing, where am I looking at? Immediate, oh, we moved the immediate, but it's just 1, isn't it? Okay. I was like, what? Yeah. So in buffer 8, okay, perfect. And operand instruction, so we go and print instruction, and yeah, that's the way. Let me see. Yep, XMM0, XMM1, 08. Perfect. Okay, let's see if we run. Let's see if we can print the other ones as well. So I go there you go, effective. We'll reset everything back, so we can go 1 turn more. Mandatory prefix %, we don't have anyone, variable blah blah blah. We go and fetch this one should go on the OXF. It's a 2-byte up table. We go there, we got it, we did it. So, and the 108 bytes, C byte, the entry should be the shield instruction as well, that's correct. And the C byte should be pointing to the mother and byte, which is 05. Yeah, that's correct. So this is the mother and byte. There we go, again operator instruction, instructing operand C byte. Fetch memory operand, mem buffer is the memory operand, that's correct. So we're moving the fetch register operand, which is gonna be the same. It's gonna reverse the same way around. Effective operand size to 4. So we just go forwards to the rec field, and my voice is getting I'm running out of my voice. Bit offset, whatever the operand name, I don't know what it is. EX, perfect. So we just go and print it out as well. And the immediate operand, let's go and find it out with the operand offset, which is 5. That's correct as well. 10b blah 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 blah, which is something else, I don't know. Let's see, the immediate buffer, it's 03. I believe it was 03. I don't remember at all. Can check it here. Yeah, 03. So it's a chill, yeah, okay. So we just do that and we print instruction. We have a shield EX03, perfect. And the last instruction as well, we reset it, blah blah blah. Mandatory prefix, we don't have it. Rex, we don't have it. We get the entry here, we can go and fetch it, blah blah blah. 1 byte, table main no byte, blah blah blah. Get index from main table, there you go. The entry, we get an entry, yeah, it's the add instruction. Begin operand, fetch memory operand, blah blah blah, mem buffer, that's correct. This is the register operand, should be EAX as well, yeah. And we have immediate buffer as well, which is nothing. Well, yeah, it's nothing because it doesn't have any immediate. You just go and print it out, and there you go. We have an add EAX. And the other thing is a story. Okay, we just run it one more time. And if we go, we have another instruction being disassembler. And the cool thing about this instruction is, well, it's the same instruction, which is well, I don't know, I mean, probably it's the same thing, but hey, you know, whenever we add another set to the family, we should celebrate. So in this case, it's good. Now we you know, we have this, we disassemble SIMD instructions as well in a really simple way, I guess, but we do it. So yeah. Okay. All right. That was a good stream, isn't it? We're filling our instruction stream full of instructions, and we are just disassembling one by one, just as we might expect to do, and that's good. Alright, so I think I'm gonna stop here. But hey, please, if you have any questions, post them on Twitter or YouTube, and I'll be there to answer. Post them questions relative to the thing we did today, if you have any questions, of course. But yeah, I would do my best to, whenever you post them, to answer them. For now, I think that will be all. And if you want to follow us and join us on the next stream, you please don't hesitate and be welcome. I think the next stream we will continue with this thing, this disassembly stuff as well. You know, we're gonna, you know, the whole task is to fill the whole instruction stream with many different instructions as well. You know, so we can see how everything gets started to construct. And yeah, so yeah. So I would say thank you very much for coming, and I will see you all on the next stream. Take care.